Hello, everyone. Thank you for joining us for today's Caringo Tech Tuesday webinar. This session is Data Resilience and Recovery in Swarm Object Storage. I'm John Bell, Senior Consultant at Caringo. Today, our guest is Caringo VP of Engineering, T.W. Cook. T.W. and I will be available to answer your questions throughout the webinar and at the end of today's presentation. In addition, we have a couple of resources available via the Attachments and Links window on your view screen. If you have any questions after the webinar, you can always reach us by email at info@caringo.com. So let's start off with a couple of quick introductions. I'll go ahead and go first. Again, this is John Bell. I've been with Caringo for over 7 years, and I'm a senior consultant based in Austin, Texas. I specialize in the design, implementation, and management of object storage. I've worked with many of our largest customers to transform their storage infrastructure with highly efficient and cost-effective object storage solutions. TW, please go ahead and introduce yourself.
Right, I'm TW Cook. I've been at Caringo for about 8 years now. I'm responsible for both the engineering group as well as customer support and training and things like that. Thanks.
Excellent. Thank you, TW. Very good. Let's go ahead and get a little bit of bookkeeping out of the way, something about Caringo. Caringo was founded in 2005 to change the economics of storage by designing software from the ground up to solve issues associated with relentless data growth. Caringo's flagship product, Swarm, decouples data from applications and hardware, providing a foundation for continued data access and analysis that constantly evolves while guaranteeing data integrity. Today, Kringle software-defined object storage solutions are used to preserve and provide access to rapidly scaling data sets across many industries by organizations such as NEP, Argonne National Labs, UK Science and Technology Facilities Council's Scientific Computing Department, Texas Tech University, US Department of Defense, the Brazilian Federal Court System, British Telecom, and hundreds more worldwide. So just a quick walkthrough of the agenda of what we're going to cover today. The main focus is going to be on the mechanics around protecting your data with replication, how data is recovered within Swarm after a failure occurs, be it a drive failure or an entire server failure, for example. We'll dive a little bit deeper into the concept of elastic content protection, where we'll touch not only on the replication pieces, but also how erasure coding data protection and recovery works. And we'll cover some key questions that you need to ask your storage vendors about recovery and how it's handled in their solutions. And we'll address any question and answers that we have from the audience. So with that said, go ahead, TW, and take it away.
Thank you, John. We've talked a lot lately about, in our blogs, about the idea of resilience, the ability for your storage system to bounce back after some kind of a failure. But for that to work, you have to understand how replication and recovery actually work, because there's some design work and some choices you have to make in order to be able to get the best benefit. The underlying principle in all of this is don't put all your eggs in one basket. Swarm will widely distribute replicas across the cluster to protect you against multiple failures. The idea of replication is really simple. You want to protect something, you make a copy of it and save it somewhere else. That way, if one of them gets damaged, you've got the other one. We have a mechanism called subclusters that let you tell us more about how your cluster is organized. So if you want to protect against the failure of a rack or a power distribution unit or switch, you could. But let's look at a typical small storage cluster. In the storage cluster, you've got a few drives. Drives fail, simple reality of our lives. And these drives have got varying amounts of stuff stored on them. If you have a replication model where you use 2 replicas, you see our little yellow object here. There's a replica of it on in two different places in the cluster. So if something happens, like that volume fails, you've still got a replica somewhere else. Now, the thing you got to think about is, what's the cluster got to do? There's more than just that replica. We have to find, in order to get us back to a fully protected state so that everything has two replicas again, we have to find that much free space in the cluster. In this little cluster, that's not going to be a problem. There's quite a bit of free space here. And we've got a lot of choices about where to put that extra replica elsewhere in the cluster. So pretty straightforward so far. But once you get a cluster that starts to be nearly full, the picture is a little bit different. If we lose that disk now, we have to find nearly a full disk worth of free space in the cluster, and it's not there. So this happens, all your data is still there. You haven't lost anything because remember there's a second replica of everything. But for the cluster to be able to reprotect your data, that idea of resilience, you're going to need some more space. It can't do it with what's there. No kind of software can do that. So there's a design issues you really have to think about.
So TW, one question for that.
Sure.
Typically, people tend to just throw things into a storage solution and not really give any, thought to it filling up. It's actually more common than not. We run into this quite frequently. I understand that there are some thresholds that you can set that will warn you ahead of time whether or not you're approaching that tipping point where you don't have enough space to recover if a unit of failure that you designed for has occurred. Could you talk about that a little bit more?
That's right, John. You can set the warning thresholds anywhere you want. So one of the interesting things is that the bigger your cluster is, the fuller you can run it. So remember that in the event of a failure, we had to find the room for a full volume to be able to recover. If you're in a pretty small cluster and you've run it, let's say you're at 90% full, you might not have enough room. If you're in a really, really big cluster with hundreds of drives, even if those drives only have like 5% of room left, you've still got plenty of space to recover from a drive failure or a second drive failure. So the number that you want to look at really depends on the size of your cluster and how much on what you want to be able to recover. If you're worried about being able to recover from the loss of an entire chassis, then that's the amount of space that has to be available in your cluster. So we provide you some reasonable defaults in Swarm, but those are customizable, and you can set those thresholds based on your loss tolerance and your idea of usage and your priorities for recovery. You can certainly run it pretty full, but you reach a point where, although you don't lose data from the first failure, the cluster can't put itself back in give it the ability to recover from a second failure. In fact, that's a good lead into some scenarios here. Let's look at this little simple case. In this one, we've got 9 objects. We've got three different nodes, each of which has a drive. We're running 2 reps. So each of those objects is replicated somewhere in the cluster. Pretty straightforward. Of course, the reality, there would be thousands, billions of objects. To make it simple, let's focus on these 9 objects. In this world, if we lost that middle node, so we've got some of the replicas are missing, we have to be able to recover. So if you look at our little green A over here on node 1, the only place to recover him, the extra replica has to go over on node 3. That's all that's left. If you look over in node 3, it's got the only remaining copy of B, so it's got to push a copy of that over to A. So before recovery, you had 6 objects per drive. After recovery, you've got 9, so you've got a 50% increase in the number of objects that are stored per drive. Throughout that process, the data is fully accessible and available, but if in the middle of that recovery and you haven't made all those replicas and you experience a second drive failure, you could lose some data.
And some of you out in the audience may notice, and TW is going to touch on this in a bit, these 2 and 3 node scenarios, things can go south very quickly. you're actually in better shape as the cluster gets larger. And I'll leave that to TW to talk about later.
Yeah, that's a good lead in. We'll actually talk about, it's a little counterintuitive, the idea that recovery is faster in a bigger cluster. But I'll show you some numbers that'll explain why that is. But let's look at the worst case here. You can run in a 2-node cluster, but if one of those nodes goes away, there's no place to recover. Yes, all your data is still there, but one more failure and it's all gone. So that's why we really encourage people to run a minimum of 3 nodes. You don't have to, but it's a smart practice. So John referred to this idea of cluster size. Let's just take a quick look. Let's suppose that you had a cluster with, to make the math easy, we're going to say 1,000 objects, and we're using 2 replicas as a protection scheme. There are lots of ways to protect your data, and we'll look at a couple of them. 2 reps is a pretty common one because it's simple to understand, pretty practical. If I've got a 3-node cluster, and I'm making 2 replicas, so I take that 1,000 times 2, I've got 2,000 objects. I've got to divide that 3 ways. I've got 667-ish of them per node. So if I lose one of them, each one of them, the remaining guys, the remaining 2, have to recover half of that 667. So they've got to recover 333 objects that they've got to re-replicate. And each one of them has only one target, one place to put them. If you take it up to a 10-node cluster, that's actually a fairly common size range, then you've only got 200 of those objects per node, and each one of those guys only has to recover 22 objects, and it has 8 choices of where to put them. So it can operate in a really parallel mode. It can send them out to lots of places in the cluster. So it stands to reason that recovery is going to go faster. But if you look at a 100-node cluster, those 1,000 objects, only 20 or so of them will be on each node. Each one of them is going to have to recover maybe 2/10. So, and they've got 98 choices of where to put it. So there's nearly no work for each of these nodes to do to recover from that. It's going to go almost instantly. If that drive fails, our ability to re-replicate all that content elsewhere in the cluster is extremely fast because of the parallelism. One of the things that makes Swarm unique is that there is not a central point of control. There's no management node that's doing this. Each volume process is actually aware of all the other volumes in the cluster. And as soon as one of them disappears because it failed or whatever, it'll immediately start the process of going through and looking at its own contents, identifying what have I got on my volume for which the only other remaining known copy was on the now gone volume, and it'll use this parallel process to recover. So it's extremely fast and it's extremely resilient because there's no single point of control. Each volume is responsible for its own contents.
Yeah. And this is a perfect example of how a scale-up, scale-out architecture would be expected to work. You would expect to be able to have recovery and resilience be much better as your node count goes up in the cluster. And TW, one observation I would make, from the field, from a design perspective, is that's the balancing act that we typically engage with our customers on and our partners on, is the balance between the desire for storage density, having an appropriate number of nodes to accommodate the failure modes that they want to be able to be resilient against, and the overall performance of what would happen when a recovery event actually takes place while they're still servicing client requests. And as those of you in the audience may surmise, having a couple of what we call elephants that have a lot of drives associated with them, that's a huge unit of failure. And you want to avoid that if you can. You kind of want that medium ground like TW has alluded to in the math, where you have a decent node or chassis count, you have a reasonable number of drives associated with it. That way, if any 1 or 2 of those goes down, it's not a huge impact on the availability of your storage, on the availability of your data, or the ability of the cluster to service requests.
Yeah, that's a great point, John. And one of the great things about Swarm is that we run on almost any hardware, but that gives you lots of choices. And this idea of designing for, you want to obviously do the most economical thing you can, and often that's a dense chassis, but you have to really look at the implications. So we spend a lot of time working with our customers to make sure that we help them make the right decisions to meet their business goals. So one of the things about Swarm, we've been talking about replication. 2 reps or 3 reps are common. 2 reps is the most common mechanism. But we also support erasure coding, the idea that instead of making copies of the object, we slice the object up and compute some parity segments. You can think of that as sort of like RAID at the object level. And when you do that, we refer to that encoding as a pair, the number of data segments and the number of parity segments. So we show here 5, 2. So we slice the object up into 5 pieces, compute a couple of parity segments. Number of parity segments is pretty important because that's the number of segments you can lose. So I can lose 2 of the data segments, 1 of the data segments, and 1 of the parity segments, and still have full access to the object. So that gives you a lot of additional ability to design resilience into your storage system. In Swarm, you can make those decisions about replication versus erasure coding all the way down to the object level. So you could decide based on a bucket or a domain maybe that belongs to a particular sub-organization. So you have a lot of control over this. You can even override that, assuming the administrator has allowed it, right down at the object level. You can mix these in the same cluster. So the part of the goal is to figure out what's the most common, to design your hardware architecture around the most common, what you believe will be the most common encoding that you're going to use. If you think about that K and P, K is the number of data segments, P is the number of parity segments. That P is the number of simultaneous volume losses that you can sustain without any data loss. K gives you control over the way the space is distributed, or the footprint. So if you get larger, one of the other trade-offs though is that the larger the K plus P is, the more resources you need. You need more nodes, you need more CPU and memory for that. So it's not completely free, although it's pretty darn efficient. So if you look at a 2-rep world, the footprint multiplier is 2 because you're basically making 2 copies. If you're storing a terabyte, it's going to take 2 terabytes to do it. And you can tolerate 1 loss failure. What that means is that if you lose a volume and it had one of those replicas, you have a period of vulnerability until recovery is completed, where if you lose the second volume with the other replica, you could lose the object. So we say you have a loss tolerance, volume loss tolerance of 1. 3 reps has a footprint multiplier of 3. You're making 3 copies, but you can lose a volume and then you can lose another volume and you still got one more copy of it. So that gives you quite a bit more protection. But if you used an 5-2, so divided into 5 segments, compute 2 parity segments, so you've got a total of 7 segments, the footprint multiplier is only 1.4. That is, you're using 1.4 terabytes to store a terabyte of data, but you still have the level of loss tolerance or protection that you had with 3 reps. So from a storage perspective, it's really efficient. You can play around with some other things. You could go up to 7.2, that gets you down to 1.3. 6.3 is a common one because that 3 parity segments means you can withstand 3 simultaneous volume losses. So it gives you a whole lot of data protection, and you're still only got a 1.5 footprint multiplier. Or if you're really space sensitive, you could do something like 11.2, which gives you really good protection for only about 1.2 times the size of the original object. So,
and TW, to your point, we're very flexible when it comes to this feature of data protection. That's why we call it elastic content protection. As you mentioned, you can run these various schemes for protecting your objects at the same time within the same cluster. There's no lock-in for the cluster that it can only run a single protection scheme and nothing else. And some of our competitors do that. They do not give you the flexibility that we do when it comes to making choices about the best way to protect the data that's coming in. I'll give you an example. So erasure coding typically is used in situations where we know that the objects are going to be very large, and we don't want to have that huge overhead that amounts from using replication to protect it. Because as you can see there in TW's chart, you go reps equals 3, with 1 terabyte requirement. Let's say it's a couple of 500 gigabyte logical objects. You're looking at a 3 terabyte footprint to store a couple of what amounts to a couple of files, which that's huge. That's a lot of storage overhead. Being able to do that with erasure coding instead brings that footprint cost down, while still providing as good as, if perhaps not, better protection than a replication model.
That's a great point, John. And there's another thing that you should think about, which is that we actually allow you to change that through time. So one of the real common use cases is someone wants to run 3 reps for the first, let's say, 90 days because they expect a lot of accesses, and so they want to be fast and efficient. But after that, their usage pattern is that it kind of goes into an archive mode, and you'd like to just protect it pretty well, but get the footprint down. So we can actually change encoding based on time, through time as you store things. So you can design a storage policy that combines the best of both worlds. Let's take a quick look at these EC scenarios, because there are a couple of extra considerations. John's already talked about the dense chassis thing, and that really plays in here. Swarm will automatically distribute segments and replicas as widely and evenly as it can to protect maximally. So it's going to try to put every one of them on a separate chassis. We use subclusters. The idea of subcluster is just a partitioning you can advise us on. So you could say all the chassis in one rack are a subcluster, all the chassis in another rack are a subcluster. And what Swarm will do is to make sure that they're distributed across that, so you can protect yourself against whatever unit of failure you feel appropriate. In this world, we've got a 5.2. 5.2 is the most common erasure coding encoding, at least among our customers. We've got 3 subclusters, each of which has 3 nodes, each of which has 1 drive. So that 5.2 means we've got 7 segments, 5 data and 2 parity, that are evenly distributed across 3 subclusters. That means 2, 2, and 3 is how it's going to land. 2 parity segments means you can loss of 2 segments. So, and if you lose those 2 segments, you can still access the object and still recover it. So in this world, when we laid this thing down, we put 2 of them on subcluster 1, 2 of them on subcluster 2, and 3 of them on subcluster 3. That's at 2, 2, and 3. Let's say we lose subcluster 2. Recovery means we've got to go push those segments somewhere else, recover them somewhere else. And we have a couple of places, only one place available to put them. So we can't fully recover you to the same level of protection because we can no longer have only 1 segment per volume. Recovery will actually work. Swarm will make a best effort, and your data will be there and you'll be protected, but it's not quite as protected as it was. So this is a design decision. As you look at 5.2, you want to look at what are the places to store those segments and what's the distribution look like after a single chassis has failed. You can change the encoding a little bit. Let's look at a 4.3 encoding. So 4.3 is still 7 segments and it's still distributed 2, 2, and 3. But in this world, we can lose any of those. If we lost that one with 3 segments on it, we've still got our object. We have the ability to recover it. Whereas in the previous one, we didn't. We still got the same challenge that we don't have enough places to put all the segments in the event of a loss. So we're not quite so protected afterward. If you had the same hardware with a 3.2 encoding, that means you're going to distribute it across with 2, 2, and 1, 5 segments, 3 plus 2. You can lose any one of these boxes and still be able to fully recover. So you can still recover it such that you have a maximum of 1 segment per volume. So this is going to get you back to a fully protected state after recovery, whereas the other 2 didn't. So those are just some considerations to think about when you're designing this stuff. It's important to not just naively assume that, well, I can put arbitrary pieces of hardware together. Swarm will try to be really smart about that and will do the best it can to protect you. But you can be smart about that and protect yourself by choosing the appropriate erasure coding and encoding for the hardware that you've got.
Hey, TW, we had
Yeah.
a question come in regarding these erasure coding scenarios. A lot of them cover the things that you need to be able to do in order to still be able to read the data out of the system. What are the ramifications for supporting write requests when you have failures of that nature, especially with erasure coding?
Well, that's a good question. So for erasure coding write to succeed, you have to meet a certain number of criteria about distribution. We actually make that configurable. So you can decide in your cluster's configuration what your tolerance for that write is. You can cause the write to require that all the segments be protected at the volume level. So maximum one segment per volume. Or you can choose node, you can choose subcluster. So that's really a decision for the level of protection that you want to achieve. We give you, by default, we do the maximum protection that we can, but we give you the ability to tune that to the way you want to lay the data out on your hardware.
And it's not just for erasure coding either. It also applies to
same thing.
Right. Replication as well. You know, for example,
exactly.
The feature we have, a replication on write, you know, being able to come back and say 2 copies were created in order for the request to succeed. Yeah.
Right, and that's a key point that we should bring out, that we're not going to go back and tell your client that's writing that it succeeded unless your data is protected at whatever level you said. If you're in a 2-reps world, we use a thing called replicate on write. It's not going to return a success to the client until both replicas have been successfully written into your cluster. Same thing for erasure coding. That object is stored and protected before we tell you that it was a successful write.
Yeah.
Any other questions?
No, thank you.
Okay. So let's go ahead. I want to summarize with some questions that everyone should be asking about recovery. A lot of people don't really think about this, but one of the things you want to think about is how automatic is recovery? Does it require manual intervention or downtime? So think of RAID rebuild times as an example of that. Some object storage systems require manual intervention and manual recovery. In our world, that's fully automatic. So we have customers with large clusters with hundreds of chassis who don't even really think about this. They'll go in on a periodic basis, let's say once a week, and take a look. Oh yeah, I've got 5 drives I need to replace. Or, oh gosh, look, that chassis is offline. I guess I should fix that. But in a big enough cluster with full automation, all of this stuff is happening without you doing anything. Your data is reprotected as fast as it can be. And that's a really important characteristic that most people don't really appreciate until it's too late. They go and buy a system and put it in, and then they realize that their enterprise is down while they deal with recovery. One of the great things about Swarm is that you really don't have to worry about that. The other question that people should be asking is the data fully accessible during recovery? There's some systems where you have to rebuild indexes and stuff to be able to find your data after a drive or a chassis failure. And again, in Swarm, all that data is fully accessible. May not be as fast because you get only one replica for you to look at, but it's there and it's accessible and it's going to work. Sort of a corollary of that is this idea of hardware configuration changes. Some of the storage systems out there have particular requirements about number of chassis, number of drives, and if those aren't met, you really have to go correct that. So what if your hardware configuration changes because a chassis went offline, or maybe because you rolled a new chassis in and you wanted to be able to add some capacity? Do you have to reconfigure, or is that going to be automatic? What you really want is to be able to just roll in another chassis, you need more capacity, plug it in, and have it automatically join your cluster, the cluster reconfigure itself, rather than you having to sit down and try to figure out a bunch of tables and stuff. And if that happens, you want the new configuration to be immediately accessible. You want it to be able to start writing on those new drives right now, because you're probably bringing it in because you're reaching the limits of being able to write. You really need that. So drives in a big cluster fail all the time. It's just a matter of mean time between failure for spinning rest storage, and your cluster needs to be able to deal with that in some way that doesn't involve you personally intervening all the time. So that's really a pretty important characteristic. Did I miss anything on that list, John?
No, I would just add to it that one of the powerful features of Swarm, for not only from this technical perspective, from a business perspective, it's a properly designed scale-up, scale-out architecture that allows you to pay as you go. Some of the scenarios that TW has outlined is you may not have your chassis completely populated with drives when you first roll out the cluster. One of the questions you may want to ask about to your vendors, and it relates to recovery, is can I hot plug volumes in as needed? Let's say a drive goes bad. Can I pull a drive out and just hot plug it in and keep on going without having to do all this manual intervention, reconfiguration, and so on? Swarm allows you to do that. Hot plug live on the fly is fully supported. There's just a lot of aspects to something being properly designed in that nature that are going to make your lives as the owners and the operators of the storage much easier as a result. And that's the goal we always have here at Caringo is to try to make this as simple and easy as possible so that you don't have to go through a lot of heavy lifting when common events like TW says, like a drive failing or a server failing, occur in your storage.
Well, that's a great point, John. And that word "possible" turns out to be important. I think you'll remember a case we had a few years ago. We had a customer that had a pretty a configuration made out of really small servers, like single one-use servers, very resilient, but not very dense. And they decided that they really needed a denser chassis to more efficiently use floor space. So they actually did the process that we've been talking about here. It's the same thing as recovery, really, but it's in a different way. They brought in a new, pretty denser chassis, introduced it to the cluster, even though it's a fairly different hardware architecture. Swarm will automatically assimilate it and distribute things out across it. Then they retired a few of the old chassis, wheeled in another one. So over the course of a couple of months, they did a complete hardware refresh into a very different style of servers without ever incurring any downtime at all. But they're taking advantage of these same features, the ability to assimilate, as you said, start small, bring in new hardware, in order to be able to make some big changes. And so this stuff works in your benefit and more than just data resilience. Makes a lot of things possible that are really hard with other systems.
Yeah. Very good. Thank you, TW.
Well, I think that's the end of my set. Did we have more questions, or?
No, it looks like our queue is cleared. Thank you again, TW. That's a great presentation. And thank you to everyone. You bet. Thank you to everyone online as well for joining us today. And if you want to keep up with Caringo, feel free to follow us on Twitter, LinkedIn, or Facebook. If you have any additional questions or would like to schedule a custom demo, please email us at info@caringo.com. And we'd also like to invite you to join us for our September Tech Tuesday webinar on September 17th, where our topic will be how to verify content integrity with Swarm object storage, which of course, that's a great tie-in to what TW has presented today. So with that said, thanks again to everybody online, and thank you, TW, and we'll go ahead and close out the call. Take care.